Let's continue on chapter 4. Today's topic is indefinite integrals. Last time we talked about calculating the antiderivatives for a definite integral and evaluating area under a curve by using fundamental theorem of calculus. So fundamental theorem of calculus was the last topic of this section. So let's mention indefinite integrals. If you remember, we had upper and lower boundaries when we were dealing with the integral. That means you were evaluating an area over a closed interval. So let's say we had a function f, and from a to b, you wanted to figure out what is this area. And you would say it is from a to b of f of x dx. And then we would find the antiderivative of f and evaluate the endpoints, subtract them from each other. But indefinite integral only asks you for the antiderivative. If given the integral of f of x dx, the capital F function is basically the antiderivative. Since there is no boundaries, you should always have a capital F function as the general antiderivative. What is the general antiderivative? It was, if you remember from 3.9, general antiderivative contains that constant c. The constant c that we add to the function. Because any constant that you add to the function, it satisfies this property that if you take the derivative of that constant, it will disappear. So this antiderivative, the capital F function, is basically the antiderivative. For example, if they ask what is the integral of x squared, we learned that the antiderivative would be a function, x cubed over 3. Because if we take the derivative of x cubed over 3, what would be the derivative of x cubed over 3? Let me write it as 1/3 x cubed. This is easier to calculate. 1/3 x cubed. What would be the antiderivative of, what would be the derivative of that? It is drag down the 3 and subtract 1 from the exponent. And what we get is simply x squared. We would get the f function, x squared. So basically 1/3 x cubed is an antiderivative. But any constant you add, 5. If I have 5 here, the derivative of that will disappear. So any constant we add, it's still the derivative of that would be simply x squared. So we would say the general antiderivative would be 1/3 x cubed plus some constancy. This is basically what we're looking for in this section, finding the antiderivative. So indefinite integral basically calculates that antiderivative function, finds the antiderivative function. Definite integral gives you a value. It doesn't give you a function. It gives you a constant number because you evaluate the function, the endpoints, and subtract them from each other. There are certain properties that the indefinite integral has. We mentioned these properties. This is properties of integral. If you have a constant multiplied by a function and you want to find the antiderivative or the integral of that, you can keep the constant outside and find the integral first and multiply the constant. It's the same as the idea of the derivative. If you have a derivative multiplied by a function, you can take the derivative, then multiply that constant. What is the antiderivative of k dx, where k is a constant? It is simply k times x, because the derivative of kx is simply k, if k is a constant. But we should add a constant c. Do not forget this constant c. The antiderivative of sine x, we should know this one. Derivative of what function is sine? Derivative of cosine would be negative sine x. So the derivative of negative cosine x is simply sine x. We add a constant c, the general solution. The derivative of what function is secant squared? Remember, tangent x has the derivative of secant squared plus c. Derivative of secant x is secant tangent. So the antiderivative or the integral of secant tangent is secant x plus some constant. If you have two functions added to each other and you want to find the integral, you can calculate the integral of each one separately, then add them together, g of x. dx. Same thing goes for the subtraction. If it was subtracted from each other, you can calculate the subtraction of each one. But it's not true for multiplication and division. Remember, for the derivatives, we had product rule and quotient rule. The same thing for the integral. You cannot simply write integral of multiplication or integral of division. We have to come up with a method to calculate those. We'll discuss that in the next sections, but at the moment we only want to find out the simple integrals. Integral of x to some power. This is, I mentioned this already, you add 1 to the exponent, divide by the same exponent, plus c. It's the opposite of what you would do for the derivative. For the derivative, you drag down the exponent and subtract 1. So here, basically you multiply. In this case, you divide by the exponent and you add 1 to the exponent. Cosine x dx, the derivative of sine x is cosine x. So the integral of cosine would be sine x. Derivative of cosecant squared, the integral of cosecant squared is cotangent x plus c, but cotangent will give you negative cosecant. So the integral of negative cotangent, the derivative of negative cotangent would become cosecant squared. Similarly, the derivative of negative cosecant x is cosecant cotangent. So the integral of cosecant cotangent is the derivative, is the negative cosecant x. Again, whatever you look at on the right side, if I take a derivative of that, negative cotangent x plus c, what do I get? Is this inside function, cosecant squared. Okay, so here are a bunch of examples. We can go through them together using these properties. Sorry, let me fix this integral notation. It's a s stretched out, something like that. So the integral of 10x to the power 4 minus 2 sine x dx. If you want to find that, one property says you can split this. I'm going to mention the properties. You can write this as the dx is just a representation that you take the antiderivative. Minus 2 sine x dx. This is just saying I can take the integral of each one separately. You can put the 10 outside if you want and find the integral of x to the power 4. If you have a coefficient, you can deal with that coefficient later. Similarly for the 2. As long as it's product, you can do this. Okay. Now what is the integral of what is the integral of x to the power 4? We know, keep the 10, add 1 to the exponent, divide by the same exponent. X to the power 5, divide by 5. Plus some constant c, minus 2 times integral of sine. Derivative of what is sine? Is negative cosine x dx. Sorry, there is no dx. Plus c. Remember, the derivative of negative cosine is sine, so therefore the integral of sine is negative cosine. And now you notice that we wrote too many c's because there is already constant here. So that's what I'm going to mention, that you don't need to write multiple constants. At the end, after you found all the antiderivatives, you can add just one constant c. That represents all the constants. Because if you add different constants together, you still have a constant. You can simplify this, by the way. This 10 and 5 will cancel out, so you get 2x to the power 5 minus times negative becomes positive 2 cosine x plus some constant. And how do you check if this is the correct integral? You take a derivative from it. Here it is, just to show you the check. Find out the derivative of 2x to the power 5 plus 2 cosine x plus some constant c. Find the derivative of that. Derivative of 2x to the power 5 and x to the 4. Derivative of 2 cosine x will be 2 times derivative of cosine, negative sine. Derivative of constant c is 0. Simplifies to 10 x to the 4 minus 2 sine x. And what is this? The starting function. So we went back and we found out that yes, these two match. So therefore, that was the correct antiderivative. This is the correct antiderivative. How about if you have cosine divided by sine squared? Now you see that here we don't have the quotient rule. You cannot use quotient rule to find the antiderivative or the integral of a function. So what we do is you try to simplify it somehow. Let me write it this way. Write it in a way that you can calculate. Cosine theta divided by sine theta. I'm going to break the sine square theta and write it this way. Sine theta. Right? Instead of sine square, I wrote it as sine theta, and d theta. This d theta just tells you what is the derivative with respect to. It's respect to theta. Theta is your variable. Okay. What if I multiply the top by 1? It doesn't really make any difference. It's still the same thing. But by doing that, I can write cosine divided by sine is cotangent. And 1 divided by sine, cosecant. Now I can answer this question. What is the integral of cotangent cosecant? Integral of cotangent cosecant. Simply negative cosecant theta plus some constant c. Do not use x. If the variable is theta, you should stick with theta. For the antiderivative, the integral would be negative cosecant theta plus some constant. Okay, how about this one? What if we want to calculate the integral of x squared plus 1 dx? What do we do? I'm gonna, again, in all these cases, we do not have quotient rule or product rule for the integral. So what do? You need to simplify it. How do you simplify? If you're dealing with fraction, one way was to do that, to look at the last example, if possible. Not always works. In this case, for that example, it worked. The other way is if you're dealing with polynomials divided by each other, normally the denominator, if the denominator has one term, this is what you do. You break it into two fractions. X squared divided by square root of x plus 1 divided by square root of x. And all has dx. Instead of square root of x, you can write it as x to the power 1/2 plus 1 divided by x to the power 1/2 dx. Okay. Now what? Now you can write x squared divided by x to the power 1/2 by subtracting the exponent from each other. It would be, remember, if you have x to the power 5 divided by x cubed, what you get is x squared, because its difference 5 minus 3 is 2. So I'm going to do the same thing. 2 minus 1/2, it would be x to the power 2 minus 1/2 is 3/2 plus 1 divided by x to the power 1/2, I can write it as x to the power negative 1/2 dx. I haven't taken the antiderivative yet. This is not the integral. This is, I tried to write it in a way that I can use the power rule, the backward power rule. Now, what would be the antiderivative? The integral of x to the power 3/2 would be add 1 to the exponent, 5/2, divided by the same thing, 5/2. Same thing. For x to the power negative 1/2, add 1 to the exponent. Negative 1/2 plus 1 is positive 1/2. I will divide by the same exponent. And if you simplify, how do you simplify? How do you get rid of these numbers in the denominator? Always multiply by the reciprocal, both in the numerator and denominator. So multiply it 2, multiply it 2. These two will cancel out. These will cancel out. So what we have is 2/5 x to the power 5/2 plus 2x to the power 1/2. You can simplify it as 2/5. X to the power 5/2 is square root of x to the 5th, and x to the power 1/2 is simply square root of x. And this is our antiderivative function. Sorry, I forgot the constant. Actually, you should have that constancy at every step. Okay. I didn't write it before that. And now, what you notice is from this step to the next, there is no integral, there is no dx. After you find the antiderivative, the integral and dx disappear. Those are just to represent that you're taking the antiderivative. Okay, here one more example. This is an example of what we learned from last time, that if you have boundaries 0 to pi over 4, you don't really need that constant. So what we do is find the antiderivative first. What would be the antiderivative of 2 sine theta? It would be 2. The antiderivative of sine theta. Derivative of what is sine? It's negative cosine. So I'll get negative 2 times negative cosine theta minus the antiderivative of secant squared. Derivative of what is secant squared? It is tangent theta. So this is evaluated from 0 to pi over 4. Again, if you have upper bound and lower bound, you don't really need that constancy. If you write the constancy, it's an extra work for yourself. So let me simplify it first. We'll have negative 2 cosine theta minus tangent theta evaluated at 0 to pi over 4. That means replace pi over 4 into the function first. You get negative 2 cosine pi over 4 minus tangent pi over 4. And subtract it from replacing 0. Negative 2 cosine of 0 minus tangent of 0. Okay, these are just numbers. Tangent of 0 is 0. Cosine of 0 is 1. Tangent of pi over 4 is square root of 2. Sorry, this is 1. Cosine of pi over 4 is square root of 2 over 2. So what we get is negative 2 times square root of 2 is negative root 2. Negative 1. And minus 2 times 1 is plus 2. And 0. So you get 1 minus square root of 2. And that's it. That's the calculation for this integral. It gives you an area under this function over the interval 0 to pi over 4. It's not specifically the area because the function is in the negative part. It's a positive part of the area minus the negative part of the area. Okay. What if the definite integral had, again, fraction? You always break it up. Later on, there would be cases that you cannot do that. But at the moment, you're going to calculate this integral, right? There's 1 divided by t to the power 3 minus 2t divided by t to the power 3 dt. And this could be simplified to 1 to 2, t to the negative 3. And 2 divided by t to the power 3 is, you can cancel out one of these, you get t squared. 2 divided by t squared is minus 2 t to the power negative 2. And dt. Now I'll find the antiderivative. The antiderivative is t to the power negative 2 divided by negative 2 minus 2 t to the power negative 1 divided by negative 1. If there was no boundary, I would add constant c, but in this case there is boundary 1 to 2. So what we get is, let me simplify it so it makes more sense. 1 divided by negative 2. T to the power negative 2 goes to the denominator, it becomes t to the power positive 2. You don't need to move the negative 2 in the denominator. That's just a constant. Minus 2 times negative 1 becomes plus 2. And t to the power negative 1 goes to the denominator, it becomes t to the power positive 1. And evaluate it from 1 to 2. Just replace 1 and 2 and subtract from each other. If we replace 2, what we get is 1 divided by negative 2 times 2 squared plus 2 divided by 2. This is replacing 2, then I subtract it from replacing 1. 1 divided by negative 2 times 1 squared plus 2 divided by 1. And what we get at the end is 1 divided by negative 8 plus 1 minus 1 divided by negative 2. So it becomes 1 divided by negative 2, and here plus 2. So if we affect this negative sign into both of them, what we get is basically plus 1/2 minus 2. And you can add up these numbers. This is 3/4 minus 1 is negative 1/4. Oh, sorry. Yeah, 3/4 minus 1 is negative 1/4. 3/8, not 3/4. There we go. Minus 5/8. Okay. I may have made a mistake in calculation. Just double check the calculation, but the idea of splitting the integral, splitting the fraction into 2 parts, that's what it's more. If you have 5 of them, if you have 5 here, you split this into 3. Okay, one last thing about in this section is, if you're given an integral, what are you finding is the antiderivative? What if they ask you to take the derivative of that antiderivative? For example, if you're given x squared, they say, what is the integral of that? Let me simply say 3x squared dx. What would be the antiderivative of that? It would be x cubed, because the derivative of x cubed is 3x squared. Then if they ask you to find the derivative of this, means find the derivative of x cubed, what do you expect is 3x squared. Taking an antiderivative and then affecting the derivative, it basically gives you the original function back. So if you start from a function and take the antiderivative, then take the derivative back, what you get is the original function. But if you rearrange the order, if you take a derivative of a function inside, so let's say if you're given x cubed and take a derivative of that, what you get is 3x squared. Then what is the antiderivative of 3x squared? It is x cubed plus some constant c. This is the only difference. If you're taking the derivative, then you take the antiderivative, there would be a constant c showing up. Because when you take the antiderivative, the general antiderivative has a constant c. That constant c with the derivative always disappears. So therefore, this dx will disappear, make that disappear. But if you rearrange the order, there would be a constant c. These two are not that complicated, but if you're dealing with the derivative inside the function, or an integral where the integral has upper and lower bound, that means it's a definite integral. And basically what you get is the derivative will give you a function where the antiderivative of that would be simply f of x, and then evaluated the two endpoints of the boundary would be f at b and f of a subtracted from each other. So why is it useful? Is in this case, if they ask you to calculate this derivative, you will get a function, whatever that function is. It is 1 divided by, let's say, 2 square root of 1 plus 3x times 3. So let's say you will get this as the derivative. So basically you want to find out what is the 0 to 1. The derivative of square root of 1 over 1 plus 3x is 3 divided by 2 square root of 1 plus 3x dx. Now what does this integral say? It says find the antiderivative. But what is the antiderivative? It is square root of 1 plus 3x. Because the derivative of square root of 1 plus 3x gave us this guy. So if you want to go backward, we simply get to square root of 1 plus 3x. Then evaluate it at the endpoints, 0 to 1. What is this theorem saying? This idea saying is, basically, you don't need to go back, take a derivative, then try to go back. if there is a derivative and an integral, basically these two kind of cancel out each other, and what you get is this simple function f. You'll get the f function. And if you have boundary, you just evaluate f at the boundaries and subtract from each other. So what we get at the end is square root of 1 plus 3 times 1 minus square root of 1 plus 3 times 0. And that is 4 minus 1, which is 2 minus 1 to 1. Okay, so the derivative and the integral acts as opposite operations of each other. Derivative and integral are like inverse operator. Well, there is a slight difference that there is a constant will show up in one of them, but the operation is exactly going backward in derivative for the integrals. Okay, this is what section 4 is. We'll continue this topic next time.